Alright, hey guys, what's going on? So today we are going to be talking about group isomorphisms. We're in the playlist of visual group theory, which is going to be an expanding playlist on basic group theory all the way to advanced group theory. So without further ado, make sure to hit that like and subscribe button. You can go into my Patreon page for the time being, where things are probably going to start moving on to YouTube now that I have all the watch hours to be able to monetize on YouTube itself. So without further ado, let's get straight into the content. Okay, so we're talking about group isomorphisms. And group isomorphisms are super important to everything that we do in advanced mathematics and in advanced physics. We're going to use this concept and use this playlist to touch into areas of advanced physics, and group isomorphisms are going to be very important for these topics later to come. So let's just lay out the basics here. That's the purpose of this video. So when all of the transformations of a group can be mapped onto all of the transformations of another group, then we say that the groups are isomorphic to each other. We could take some very simple cases. So we're going to go through a couple of examples here, and we're going to see what exactly group isomorphisms are visually speaking. Okay, so let's consider this symmetric group S2. Okay, this S2 group has two elements in it. It has the identity element where 1 goes to 1 and 2 goes to 2. Nothing super crazy there. But then we have the transposition group, or the transposition transformation, where 1 goes to 2 and 2 goes to 1. So I and T are the elements in S2. So one way we can write this is to say, I'll write it right here, S2 is equal to the set, make that a little bit nicer looking. S2 is equal to the set of the identity transformation and the transposition transformation. Okay? And so now, so we have these two transformations that make up the set of S2. To make it a group, again, we have to obey a couple of axioms. The first axiom is closure. So let's write that down. Let's write it down right here. Closure. Associativity. It has to contain the identity. And it has to have an inverse. Alright, so these are all the properties of a group. We need to keep these in mind when we go on to more advanced stuff, because oftentimes basics gets sort of washed out of the brain as we start trying to understand more advanced stuff, but we cannot have that happen because this is really important for us to be able to really come back to the roots and the basics of what groups are. Closure, again, we can talk about all of these in terms of these tables. So closure means that whenever you have one transformation and you follow it with another transformation in the group, you get a transformation in the group back, right? So take, for example, transposition composed with the identity group, you get the transposition back. Okay, this is part of the group, so we have closure. And we'll see later on how closure can be applied to more advanced groups. Okay. Associativity means that it's sort of groups that only have two elements in it are quite easy to show, but say groups that have three elements in them, we'll talk about this one in a few seconds here. But the point here is that say you have transformation A, and then after you have transformation B, and then after you have transformation C, that should be equal to the same thing if you do them in different orders, right? So that's the associativity law, okay? And then the identity rule just means that there needs to be an identity in the group, and the inverse rule means that there needs to be an inverse. In other words, an element in the group that takes you back to the identity. Okay? Alright, so when we take a look at this table, we have the results here. So I composed with I gives us I, and then transposition composed with I gives us transposition. I composed with transposition gives us this, and then so forth. Okay? And so now let's consider a new group, G, where on G we have a different operation. This is a multiplication, transformation. Right? So these are actually kind of the same. I have them. The point here is that these can also be different. Okay? As long as the structure of the group, or the characteristic table here, is the same as the structure of the characteristic table here, then we are good to go. We can call these things isomorphisms. And we could see that -1 times -1 is +1. +1 times -1 is negative. And you can see how this transposition table is equal, or not equal to, but very similar in structure to this characteristic table. Okay? So we can see that there's a clear one-to-one mapping between each element in these groups, where I is associated with +1 and tau is associated with -1. Okay, so I gets mapped to +1, tau gets mapped to -1. Oftentimes when you're watching videos on group theory, you'll see these weird arbitrary spaces that people draw out to show that these groups sort of inhabit a space, if you will. Okay. I personally don't really like this way of showing things, but I'm showing it to you just to help you understand anything else that you might see in other videos or other books. Okay? So let's talk about some more complex groups. Let's take the permutation group P3. Okay? Permutation group P3 is going to consist of 6 elements. I've excluded one of them because it's just the identity, and so we have the 5 here. So we have we have P1, P2, P3, and P4 and P5. And what we want to do here is we're going to permute. We're going to make all the different possible permutations of this group of, say, tennis balls. And these are the balls in containers, okay? We have, 2 going to 3, 3 going to 2, and then 1 going to 1, 1 going to 2, 2 going to 1, and 3 going to 3. And you can read these off. These P3, P4 are cyclic permutations, and we'll see that there's going to be some isomorphisms with this guy here. But let's just cover this really quick. P5, P2, and P1 are swappings, right? So 1 swaps with 3, 2 swaps with 3, and 1 swaps with 2. And so these are all the different possible permutations that we have for this group P3, okay? The table for this looks like this, okay? I'm not going to go through all of this because I think you could probably do this on your own, but let's just take one example. Say we have P2 followed by P1, okay? We're saying that this gives us P4. So P2, 1's going to go to 2, followed by P1, 2 is going to go to 3, so that means the net result is 1 going to go to 3, and then we have 2 going to 1, and then 1 going to 1, so 2 goes to 1. So 1 goes to 3, 2 goes to 1, we have P4, okay? So we just explained this one here, but we can do this all by hand if we want. We just have to take all these groups, and we start with one permutation, we do another permutation, and then we see what the net result is. Okay. So again, these tables get really complex, and there's something that I want to point out here when we start talking about the dihedral group, which is that the order of these actually matters if you want to make the the isomorphism visually obvious to us, and we'll see this in a few seconds. So let's now consider the dihedral group D3. Okay, so the dihedral group D3 is going to consist of rotations, okay, of say a triangle or some sort of not parallelogram, but some sort of geometric shape that has 3 apices. And what we can do is we could say in the dihedral group we have rotations, which is what I'm illustrating here with the arrows, but we also have reflections, right? So when we say reflection 1 means a reflection in this vertical reflection. So if we were to say draw a line here, reflection 1 is a reflection in this way. Reflection 2 is going to be a reflection in this way, and then reflection 3 is through the other apex. Okay, so we have reflections, three reflections, and 2 rotations. Look really quick for a second here at this group. We have 3 swappings, P1, P2, and P5, and then 2 cyclic permutations. Right, so that's going to be P3 and P4, and you can write this out if you want to. Rotation 120 degrees and rotation 240 degrees is going to be associated with P3 and P4. And then reflections are going to be associated with P1, P2, and P5. Okay. And so when we organize our table in this way here, where we have I, R1, R3, and R2, same thing going down this way, then we can see here that we map P1 to R1, P2 to R3, P5 to R2, P3 to the rotation of 120, and P4 to rotation of 240. See P4, rotation 240. We said P2 is P5, right? So we can actually see here that every one of these guys, there's a mapping, right? So we're saying P1 is getting mapped to R1. So P1 is getting mapped to R1. And then P2 we're saying is getting mapped to R3. P2 is getting mapped to R3. And then let's do a different color. P3 is getting mapped to R120. And then P4 is getting mapped to R240. And then P5 is getting mapped onto R2. So there's a 1-to-1 mapping. When we look at the structure of these 2 characteristic tables, we see that there's a 1-to-1 relationship, which means that permutations are isomorphic to rotations and flips of a triangle. Right? So we can begin to see how this is actually quite deep. Say we have P1, so say we have 3 tennis balls. Okay, and we label the tennis balls in these tennis ball holders, okay, and we can say, well, all the possible permutations that I can do with these tennis balls are encoded in rotations and reflections of a triangle. That's not an obvious thing to say, right? But nevertheless, we can see that permutations are really just the same thing as rotations and reflections of a triangle, or the D3 group. Okay, now I've highlighted in yellow some of these, These are subgroups, and subgroups are going to be the topic of our next video. But subgroups, just as a teaser, they are groups. They have the identity, they have inverses, and they have they obey closure. You can see here R1, 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 I, and I, so they obey a closure. They are associative, they have inverses, so they obey all the rules, all the axioms of groups, but they are within groups themselves, right? So that's a subgroup, and we're going to talk about that a little bit more in our next video. We're going to go deeper into subgroups. Okay. Last but not least, let's take a look here that the real numbers under addition are isomorphic to positive real numbers under multiplication. This is not too difficult to see. So we're going to say this is our group, all the real numbers under addition. They obey closure, they're associative, there's an identity, and there's an inverse, right? So the identity for addition is going to be 0. That's going to be 2 plus 0 is 2. So identity, again, is to do nothing. The inverse is going to be the negative, right? So 2 plus negative 2 is going to give us 0. So that's the inverse. So inverses are negative numbers. I'll just write that. Negative numbers. Identity is 0. And then associativity and closure. All numbers obey those rules. And then we have, and we're saying that they're isomorphic to this group here. So we're now restricting ourselves to positive real numbers under multiplication. Again, these are, they obey closure, it obeys associativity, as we know. There is an inverse, or there's an identity, right? So the identity is 1. That's a positive real number. Anything times 1 is going to be, it's going to be that thing again. So 2 times 1 is 2, 3 times 1 is 3. And then there's an inverse, right? So the inverse is going to be, it's a positive real number. It's going to be 1 over whatever number we're multiplying by. So 2 times 1/2 is 1. 3 times 1/3 is 1, right? So those are our inverses. And we can say here that the positive real numbers, so we consider a map now. This is our isomorphic mapping. That the real numbers under addition, this map is going to take all the real numbers under addition, and it's going to map them to all real numbers under multiplication. And this map is going to be, you take any number in R, say, let's take 2 for example, it's going to map it on e to the 2 power, or e to the e squared, right? So let's take, for example, 2. So phi of 2 is equal e to the 2, and you can see that 2 plus 2 is going to be 4, right? So 2 on this side here, let's do 2 plus 2 is equal to 4. When we multiply e to the 2, well, that's e to the 4. Right, so this is under multiplication, this is under addition. And we can see that we do indeed, this actually works because this 4 is now mapped to this e to the 4. Right, so this mapping here. So we can actually see that this is indeed an isomorphism. So under this mapping we can see that it clearly shows multiplication is isomorphic to addition under a subset of the real numbers. The last thing I want to add is that there's a topic called an isomorphic class. Isomorphic classes are going to be the groups that are all isomorphic to each other. So, say P3 and D3, right, they fall under a class, right? So a class and P3 and D3 fall under a class because they're isomorphic to each other. The point here is that we can't identify all of the possible groups under one particular class. There could be an infinite number of groups because we could quite literally invent our own symbols and construct a characteristic table out of those symbols to resemble that of a P3 group. Okay. So what we're interested in actually is all of the possible isomorphic classes that we can think of, not all of the individual groups themselves that fall under different isomorphic classes. So that's the point. That's the whole enterprise of group theory. With that being said, I hope you guys enjoyed this content. Make sure to hit that like and subscribe button, and I'll see you guys in the next video. Bye.